We have seen several different cryptographic ideas, right? So public key cryptography, such as RSA, we've seen it be useful for two main reasons. First, it helps with secure key exchange. So Alice can use Bob's public key to send something that only Bob can decrypt, right? Second, it gives us digital signatures. So Alice can use her secret key to sign a message, and anyone can verify that the signature, so they can verify the signature using Alice's public key. And so public key cryptography helps with both secrecy and the authentication part. However, so one of the big issues is that public key cryptography is relatively slow. It is not usually the best choice for encrypting very large messages or large files. All the operations we're doing can actually be quite expensive if your messages are very big. So on the other hand, we had symmetric key cryptography, such as AES. And one of the nice things about that is that it's fast and efficient. And so this is what we want for encrypting large amounts of data. But it had a problem, right? So symmetric key cryptography had the problem that Alice and Bob need to already share the same secret key. So what's generally done in practice is that you actually combine these schemes. So you use public key cryptography to establish and protect the shared key. So the idea is that instead of using the public key cryptography to communicate messages, you use it to communicate a secret key, and then that secret key is used with a symmetric key crypto system so that the data can then be sent efficiently. And so this is how it's generally done in practice, right? And so the public key part is usually used at the beginning to establish trust or agree on a session key, and then the symmetric key is used for the actual communication. So in other words, modern crypto systems, it's not usually just like RSA or just AES. It's a combination of these tools. And so let's look at an example of how something like this could work, right? So first, Alice and Bob each generate public key pairs, right? Alice has a public key A here for Alice, and a secret key for Alice, and Bob has a public key for Bob here and a secret key for Bob. And of course, these are public, and then Alice keeps her own secret key and Bob keeps his own secret key. And so now suppose Alice wants to send encrypted data to Bob. So instead of using RSA to encrypt the entire message, what Alice first does is she generates a random symmetric key. And so this is going to be the session key. So think of it like this. Alice is going to generate a key that is going to be used later with AES or something like that, some symmetric, like efficient symmetric crypto system. And then what's going to happen is Alice is going to encrypt and sign her key. So what does that mean? So she will use Bob's public key to encrypt the key. So this way no one learns this. But also she is going to sign the message that she is sending with her own. So she uses her secret key to do the digital signature of the message. So in that way, when she sends her ciphertext together with the signature, only Bob can find out what the ciphertext is, but he can also verify that no one modified the ciphertext that was sent to him, right? So you do both things at the same time, so you have like the secure communication, but also with authentication at the same time. And with this, Bob can decrypt the session key. So Bob has the secret key, and he can then decrypt the session key. And of course, he verifies that this is indeed Alice that was sending to him, not someone else, not someone pretending to be Alice. He knows that Alice sent this, and now he can actually see what the session key is. Now, so now Alice then encrypts the message that she wants to send. So the message now is a bigger message, right? and she encrypts it using AES. So now she uses like something like AES to encrypt the message. And again, she signs what she sends. So every time she's sending something, she's using her digital signature. So she signs what she is sending, and she sends this to Bob. So then, of course, Bob first verifies that this is indeed Alice sending him this ciphertext C. And once that verification is done, he can now decrypt the ciphertext with the key that they had shared before, right? And so with this, he's able to obtain the message. And so in practice, the modern systems they use this authenticated encryption, where encryption and authentication are combined into one method, right? And also they mix up. They use both public key cryptography to handle the keys and the identity, and then they use symmetric key cryptography to encrypt the data efficiently, right? So it's essentially a mix of everything we've seen in this lecture. And even that is, I mean, we've seen a lot of simplifications. In practice, there are so many details that one needs to take care of. But at a high level, this is essentially what's going on. And these are the type of tools and what it can look like to be doing these things. And so finally, let's talk about a major challenge for modern cryptography, which is quantum computing. So we saw that RSA is sort of secure under some type of computational assumption. And we saw also that the whole idea was that you had this number n, which is equal to p times q, and that if you know p times q, it's easy to come up with the secret key. So if you're able to factor large numbers efficiently, you can essentially break RSA. And the thing is that uh, uh, indeed, if you have a quantum computer, there is an algorithm called Shor's algorithm that actually factors large integers efficiently, so in polynomial time. And so this is the direct threat to RSA. And and so if someone were ever to build a large enough quantum computer, it would essentially break RSA. And so that's why you have a lot of interest nowadays on what's called post-quantum crypto, which is schemes that we do not know of ways in which a quantum computer can break them, right? So this is the big place where quantum computing has an effect in crypto, is in breaking RSA and some other schemes also, which are based on these type of things. The impact of quantum computer on AES is much less. There is something called Grover's algorithm that can essentially speed up what would be like trying to guess a key, but it's not something that is like polynomial time. It essentially reduces the size of the key by half, the key search space. And so what's happening in practice is that we are like, it's just recommended that you use larger key sizes. So let's say where once before it was common to use a 128-bit key, now the recommendation is to use something like 256-bit key. And so the main idea for is just to say that advances can actually change the way we look at the crypto stuff, right? So a lot of the stuff done in public key cryptography nowadays is related to this threat of quantum computing. There's also other types of threats. You have like AI threats also. So how does AI affect crypto and so on? And so lots of interesting problems to work on there.